Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Achronix with Quinn Jacobson, who's going to talk today about IP security in FPGAs. Quinn, what sort of problems are you starting to see with security in FPGAs?
IP vendors today are taking their designs and putting them into FPGAs. That design represents likely their core IP and the most valuable asset to their company. We want to make sure that when they put that design into the FPGA, that no one can reverse engineer and that their competitors or their customers can't see the actual design itself.
How much of a problem is that? Is it a concern at this point, or is it actually showing up as real problems?
This is a real problem. And if you're a company that has invested in this IP development, there's absolutely no way you're going to deploy it unless you have complete assurance that that design is going to be protected.
So is it really just about protecting the IP? Is it about authenticating it? Where do you draw the line here?
It's not just about protecting the IP from reverse engineering. Equally important is authenticating the design so that when you build a system with an FPGA, you know the design running the FPGA is a design that came from you as the IP vendor, and that no one has either manipulated that design or replaced that design with something else that may act as a Trojan in your system.
Why don't you draw this out for us?
Happy to.
So what are we looking at here?
Okay, so here we have a chip with an FPGA fabric in it. This might be a discrete FPGA chip, or this might be an SoC where the FPGA is an embedded FPGA core. And here we have a user's design, very simple one here, but this could be as complex and represent whatever algorithm the IP vendor wants to implement in hardware.
So what happens when that gets loaded into the FPGA?
So the IP vendor wants to load their design into the FPGA fabric. And so we want to make sure that we can protect that. So of course they're going to want to encrypt that with some sort of encryption. And then we will decrypt it as it's pulled onto the FPGA.
Is the concern here that somebody's going to steal the IP, or is the concern that they're actually going to use that as a backdoor and manipulate the IP somehow?
So we're protecting against both someone who may observe the IP in transit. So this design, one of the things about FPGAs is not only can you render your design to hardware, but you can even push updates out to the field. So this might be stored on a flash or even pushed out over the internet to the FPGA. So we want to make sure that the design is no one can see it as it's being in flight, and that whatever the IP vendor intended is actually what's delivered here. So it's not only encryption, we need to sign that with some sort of authentication so that we can authenticate that as it comes into the FPGA.
Let's drill down into this a little bit. How does this actually work?
So let me take a step back here and go through the actual details of how this works end to end. So it actually starts with the user needs to put a key onto the FPGA into some fuses. Now we could load a key into the FPGA and these fuses can't be read, so that'd be pretty safe. But if you had an attacker that had access to maybe a few tens of millions of dollars worth of equipment and had enough time, they can actually cut open that chip and see those fuses. So we actually need to do better than that. So what we actually do is we put a key derivative function, which is some sort of encryption algorithm here, and we don't actually store the key itself in the chip. We actually store only an encrypted version of that, where we use what is called a physically unclonable function, or a PUF, which is actually a randomly generated number in this chip that's unique to this chip based on random variations in the physics of this chip.
And one of the things about a PUF is that, and particularly a random number generator, is that if you actually do break into the chip, this is the only chip you get into, not all the chips like this, right?
So yes, this is unique to this chip and only this chip. And the chip manufacturer, the foundry, no one actually can see this. And the really cool thing about a physical PUF is that it is a function of the silicon properties, the random variations in doping in silicon. And so if you were to actually start tampering with this, you would actually change the physical structure and therefore destroy the PUF. So it's actually naturally tamper resistant. So there's no practical way to get the puff out even by cutting the chip open.
And what you've done here is both secure the data in transit, the IP itself, as well as when it's in place, right? So it's secure both places.
Yes, so we're going to take this key in our encryption function, and we use in the industry mostly it's like 256-bit AES GCM as the encryption algorithm, and that's sort of what you'd see in your high-end VPN or TLS. And the cool thing about AES GCM as an encryption algorithm is that it not only encrypts the data with a very strong encryption algorithm, but it also is inherently an authenticator. So when AES, it basically does both a encrypt and sign and a decrypt and authenticate in one step by the algorithm. Now, in modern systems, we are even more paranoid because we worry that someone's going to do some sort of side channel attack to try to crack the code on the AES. So today, all the leading FPGA vendors, we do a number of ways to do further protection than just the inherent AES, which is plenty secure to store the data data in flight. But to protect it while it's being decoded, we actually do two primary defenses. One is we break the design into lots of little segments, and we actually then we derive a set of rotating keys for each segment. So actually this is using many, many different keys as it's decrypting. In addition to that, we have a whole bunch of hardware that protects this AES algorithm from any sort of dynamic power analysis attack.
Where are you seeing the most concern for this? Is it, say, automotive and medical and aerospace, or is it other markets as well?
It's everyone. So if you're doing a secure endpoint for a aerospace or military application, this is critically important to protect your algorithms. Equally though important is if you have a new AI algorithm for doing speech recognition, that algorithm itself may be worth hundreds of millions or billions of dollars. You want to make sure that your competition can't see how your algorithm internally works.
So what else has to be done to secure this?
So if your design is secure in flight, we also need to make sure once we load it into the FPGA fabric that there is no backdoors to observe the inner workings of this. So before we'd even load anything in here, we're first going to lock all of the debug or testing ports and lock down this fabric to make sure that before the design is loaded on it, there's no way to read out any internal state from it or observe its inner workings. In addition to that, hackers are like velociraptors. They're going to check they're going to probe the fence. So we don't want them poking. Now we have no weaknesses here, but we don't want them poking around. So we're going to even put an extra protection, which is we'll put a door here with a public key. And so a IP vendor can have their private version of that private public key for RSA encryption. And we're not even going to activate any of this unless the design itself is signed with a public key.
How much complexity does this add to the design process?
How much complexity? I mean, from the IP vendor's perspective, as they're designing this, the tools will basically, you can set a flag and the tool will automatically go through all this thing of encrypting and signing the thing. Now, there's a, reasonably complex system here, but in a modern process, this is you can't even find this on the FPGA chip.
How about overhead for security? How much is there? Does it take up space? Does it take up resources on the chip?
It takes a very small fraction of the chip. So this is a tiny fraction compared to the other blocks you'd have. So this would be orders of magnitude smaller than the fabric or if this is an SoC, any of the processor cores or other logic you'd have in this chip.
How does this compare to design, for example, in an ASIC?
That's a good question. So from an IP vendor's perspective, the FPGA solution can actually be more secure than them creating a custom ASIC. Because if they create a custom ASIC, that design is exposed, in the manufacturing process, a lot of players involved in the manufacturing, the handling of those chips. And any one of those, in theory, can go and reverse engineer the circuits out of the ASIC. One of the very powerful things about an FPGA solution is that the FPGA itself is a blank slate. When it's manufactured, there's nothing secretive or exposed in the FPGA fabric. And you as an IP vendor can wait and load your super secret part at the very last minute in a secure way.
And to some extent, you've changed the economics of why people buy security, right? So the consumers were never willing to pay for it, but the IP vendors who have a stake in this, they are potentially willing to say, I'm only going to go to a chip that's secure.
Yes, and there's other reasons why you want to go to FPGA in order with all these algorithms that are constantly evolving, and you want to be able to, as a new, better version algorithm, you want to have data path efficiently executing it, but you want to be able to upgrade it. But in addition to that, we believe FPGAs, provide the most secure solution for IP vendor to protect that most core asset of theirs.
Quinn Jacobson, thanks for a great explanation.
Thank you very much.